In this video, we will be covering NumPy in 1D, in particular ND arrays. NumPy is a library for scientific computing. It has many useful functions. There are many other advantages like speed and memory. NumPy is also the basis for pandas, so check out our pandas video. In this video, we will be covering the basics and array creation, indexing and slicing, basic operations, universal functions. Let's go over how to create a NumPy array. A Python list is a container that allows you to store and access data. Each element is associated with an index. We can access each element using a square bracket as follows. A NumPy array, or ND array, is similar to a list. It's usually fixed in size, and each element is of the same type, in this case integers. We can cast a list to a NumPy array by first importing NumPy. We then cast the list as follows. We can access the data via an index. As with the lists, we can access each element with an integer and a square bracket. The value of A is stored as follows. If we check the type of the array, we get numpy.ndArray. As NumPy arrays contain data of the same type, we can use the attribute dType to obtain the data type of the array's elements, in this case a 64-bit integer. Let's review some basic array attributes using the array A. The attribute size is the number of elements in the array. As there are 5 elements, the result is 5. The next two attributes will make more sense when we get to higher dimensions, but let's review them. The attribute ndim represents the number of array dimensions or the rank of the array, in this case 1. The attribute shape is a tuple of integers indicating the size of the array in each dimension. We can create a NumPy array with real numbers. When we check the type of the array, we get numpy.ndArray. If we examine the attribute dType, we see float64 as the elements are not integers. There are many other attributes. Check out numpy.org. Let's review some indexing and slicing methods. We can change the first element of the array to 100 as follows. The array's first value is now 100. We can change the fifth element of the array as follows. The fifth element is now 0. Like lists and tuples, we can slice a NumPy array. The elements of the array correspond to the following index. We can select the elements from 1 to 3 and assign it to a new NumPy array, D, as follows. The elements in D correspond to the index. Like lists, we do not count the element corresponding to the last index. We can assign the corresponding indices to new values as follows. The array C now has new values. See the labs or numpy.org for more examples of what you can do with NumPy. NumPy makes it easier to do many operations that are commonly performed in data science. These same operations are usually computationally faster and require less memory in NumPy compared to regular Python. Let's review some of these operations on one-dimensional arrays. We will look at many of the operations in the context of Euclidean vectors to make things more interesting. Vector addition is a widely used operation in data science. Consider the vector u with 2 elements. The elements are distinguished by the different colors. Similarly, consider the vector v with 2 components. In vector addition, we create a new vector, in this case z. The first component of z is the addition of the first component of vectors u and v. Similarly, the second component is the sum of the second components of u and v. This new vector z is now a linear combination of the vector u and v. Representing vector addition with line segment or arrows is helpful. The first vector is represented in red. The vector will point in the direction of the 2 components. The first component of the vector is 1. As a result, the arrow is offset 1 unit from the origin in the horizontal direction. The second component is 0. We represent this component in the vertical direction. As this component is 0, the vector does not point in the horizontal direction. We represent the second vector in blue. The first component is 0. Therefore, the arrow does not point to the horizontal direction. The second component is 1. As a result, the vector points in the vertical direction 1 unit. When we add the vector u and v, we get the new vector z. We add the first component. This corresponds to the horizontal direction. We also add the second component. It's helpful to use the tip-to-tail method when adding vectors, placing the tail of a vector v on the tip of vector u. The new vector z is constructed by connecting the base of the first vector u with the tail of the second v. The following 3 lines of code will add the 2 lists and place the result in the list z. We can also perform vector addition with 1 line of NumPy code. It would require multiple lines to perform vector subtraction on 2 lists as shown on the right side of the screen. In addition, the NumPy code will run much faster. This is important if you have lots of data. We can also perform vector subtraction by changing the addition sign to a subtraction sign. It would require multiple lines to perform vector subtraction on 2 lists, as shown on the right side of the screen. Vector multiplication with a scalar is another commonly performed operation. Consider the vector y. Each component is specified by a different color. We simply multiply the vector by a scalar value, in this case 2. Each component of the vector is multiplied by 2. In this case, each component is doubled. We can use the line segment or arrows to visualize what's going on. The original vector y is in purple. After multiplying it by a scalar value of 2, the vector is stretched out by 2 units, as shown in red. The new vector is twice as long in each direction. Vector multiplication with a scalar only requires 1 line of code using NumPy. It would require multiple lines to perform the same task as shown with Python lists as shown on the right side of the screen. In addition, the operation would also be much slower. Hadamard product is another widely used operation in data science. Consider the following 2 vectors, u and v. The Hadamard product of u and v is a new vector z. The first component of z is the product of the first element of u and v. Similarly, the second component is the product of the second element of u and v. The resultant vector consists of the entry-wise product of u and v. We can also perform Hadamard product with 1 line of code in NumPy. It would require multiple lines to perform Hadamard product on 2 lists as shown on the right side of the screen. The dot product is another widely used operation in data science. Consider the vector u and v. The dot product is a single number given by the following term and represents how similar 2 vectors are. We multiply the first component from v and u. We then multiply the second component and add the result together. The result is a number that represents how similar the 2 vectors are. We can also perform dot product using the NumPy function dot and assign it with the variable result as follows. Consider the array u. The array contains the following elements. If we add a scalar value to the array, NumPy will add that value to each element. This property is known as broadcasting. A universal function is a function that operates on ND arrays. We can apply a universal function to a NumPy array. Consider the arrays A. We can calculate the mean or average value of all the elements in A using the method mean. This corresponds to the average of all the elements. In this case, the result is 0. There are many other functions. For example, consider the NumPy arrays B. We can find the maximum value using the method 5. We see the largest value is 5. Therefore, the method max returns a 5. We can use NumPy to create functions that map NumPy arrays to new NumPy arrays. Let's implement some code on the left side of the screen and use the right side of the screen to demonstrate what's going on. We can access the value of pi in NumPy as follows. We can create the following NumPy array in radians. This array corresponds to the following vector. We can apply the function sine to the array x and assign the values to the array y. This applies the sine function to each element in the array. This corresponds to applying the sine function to each component of the vector. The result is a new array y, where each value corresponds to a sine function being applied to each element in the array x. A useful function for plotting mathematical functions is line space. Line space returns evenly spaced numbers over a specified interval. We specify the starting point of the sequence, the ending point of the sequence. The parameter num indicates the number of samples to generate. In this case, 5. The space between samples is 1. If we change the parameter num to 9, we get 9 evenly spaced numbers over the interval from -2 to 2. The result is the difference between subsequent samples is 0.5 as opposed to 1 as before. We can use the function linspace to generate 100 evenly spaced samples from the interval 0 to 2π. We can use the NUMPY function sign to map the array X to a new array Y. We can import the library pyplot as PLT to help us plot the function. As we are using a Jupyter notebook, we use the command matplotlib inline to display the plot. The following command plots a graph. The first input corresponds to the values for the horizontal or x-axis. The second input corresponds to the values for the vertical or y-axis. There's a lot more you can do with NumPy. Check out the labs at numpy.org for more. Thanks for watching this video. We can create NumPy arrays with more than one dimension. This section will focus only on 2D arrays, but you can use NumPy to build arrays of much higher dimensions. In this video, we will cover the basics and array creation in 2D, indexing and slicing in 2D, and basic operations in 2D. Consider the list A. The list contains 3 nested lists, each of equal size. Each list is color-coded for simplicity. We can cast the list to a NumPy array as follows. It is helpful to visualize the NumPy array as a rectangular array. Each nested list corresponds to a different row of the matrix. We can use the attribute ndim to obtain the number of axes or dimensions referred to as the rank. The term rank does not refer to the number of linearly independent columns like a matrix. It's useful to think of ndim as the number of nested lists. The first list represents the first dimension. This list contains another set of lists. This represents the second dimension or axes. The number of lists the list contains does not have to do with the dimension, but the shape of the list. As with the 1D array, the attribute shape returns a tuple. It's helpful to use the rectangular representation as well. The first element in the tuple corresponds to the number of nested lists contained in the original list or the number of rows in the rectangular representation, in this case 3. The second element corresponds to the size of each of the nested lists or the number of columns in the rectangular array 0. The convention is to label this axis 0 and this axis 1 as follows. We can also use the attribute size to get the size of the array. We see there are 3 rows and 3 columns. Multiplying the number of columns and rows together, we get the total number of elements, in this case 9. Check out the labs for arrays of different shapes and other attributes. We can use rectangular brackets to access the different elements of the array. The following image demonstrates the relationship between the indexing conventions for the list like representation. The index in the first bracket corresponds to the different nested lists, each a different color. The second bracket corresponds to the index of a particular element within the nested list. Using the rectangular representation, the first index corresponds to the row index. The second index corresponds to the column index. We can also use a single bracket to access the elements as follows. Consider the following syntax. This index corresponds to the second row, and this index the third column. The value is 23. Consider this example. This index corresponds to the first row, and the second index corresponds to the first column, and a value of 11. We can also use slicing in NumPy arrays. The first index corresponds to the first row. The second index accesses the first 2 columns. Consider this example. The first index corresponds to the last 2 rows. The second index accesses the last column. We can also add arrays. The process is identical to matrix addition. Consider the matrix X. Each element is colored differently. Consider the matrix Y. Similarly, each element is colored differently. We can add the matrices. This corresponds to adding the elements in the same position. i.e. adding elements contained in the same color boxes together. The result is a new matrix that is the same size as matrix Y or X. Each element in this new matrix is the sum of the corresponding elements in X and Y. To add two arrays in NumPy, we define the array in this case X. Then we define the second array Y. We add the arrays. The result is identical to matrix addition. Multiplying a NumPy array by a scalar is identical to multiplying a matrix by a scalar. Consider the matrix Y. If we multiply the matrix by this scalar 2, we simply multiply every element in the matrix by 2. The result is a new matrix of the same size where each element is multiplied by 2. Consider the array Y. We first define the array. We multiply the array by a scalar as follows and assign it to the variable z. The result is a new array where each element is multiplied by 2. Multiplication of two arrays corresponds to an element Y's product or Hadamard product. Consider array X and array Y. Hadamard product corresponds to multiplying each of the elements in the same position, i.e. multiplying elements contained in the same color boxes together. The result is a new matrix that is the same size as matrix Y or X. Each element in this new matrix is the product of the corresponding elements in X and Y. Consider the array X and Y. We can find the products of two arrays X and Y in one line and assign it to the variable z as follows. The result is identical to Hadamard product. We can also perform matrix multiplication with NumPy arrays. Matrix multiplication is a little more complex, but let's provide a basic overview. Consider the matrix A, where each row is a different color. Also, consider the matrix B, where each column is a different color. In linear algebra, before we multiply matrix A by matrix B, we must make sure that the number of columns in matrix A, in this case 3, is equal to the number of rows in matrix B, in this case 3. For matrix multiplication, to obtain the ith row and jth column of the new matrix, we take the dot product of the ith row of A with the jth columns of B. For the first column, first row, we take the dot product of the first row of A with the first column of B as follows. The result is 0. For the first row and the second column of the new matrix, we take the dot product of the first row of the matrix A, but this time we use the second column of matrix B. The result is 2. For the second row and the first column of the new matrix, we take the dot product of the second row of the matrix A with the first column of matrix B. The result is 0. Finally, for the second row and the second column of the new matrix, we take the dot product of the second row of the matrix A with the second column of matrix B. The result is 2. In NumPy, we can define the NumPy arrays A and B. We can perform matrix multiplication and assign it to array C. The result is the array C. It corresponds to the matrix multiplication of array A and B. There is a lot more you can do with it in NumPy. Check out numpy.org. Thanks for watching this video.